laboratory. We have not had the chance to publish these results yet, but we will do that with the process of doing this. Another thing we're looking into is the comparison of ultrasonic and lower frequency wave speeds over a range of applied stress and angles. This is evaluation of the geophysical properties of Montney Shale. Again, we had to rely on Montney Shale because US core is very difficult to obtain. Companies do not want to part with this. The cores that we use, the oriented Montney cores, have a single open fracture, and this is oriented according, well, it depends on how you take the core. They also have multiple hairline cracks, which we don't know if they're not native or it was stress release fracture development after we took the core out of its natural bed. So you see we have different angles over there, 0, 45, 90 degrees. Look at the length, diameter, the density for the air dry sample. Of course, the density of the water saturated system and the fracture void ratio, and we investigated how the system behaves under these conditions. Well, to make a long story short, what you see happening over here is that the S wave, we don't care, basically we see very little effect of whether this is dry or fully saturated. However, we see that the P wave shows a distinct, a very, very different behavior if it is dry or saturated. The solid lines are the water-saturated cores, and they can show higher velocities over there, and S-wave velocities, whereas the dotted lines, the broken lines, are room-dry cores, and there you can see that that we have much lower velocities. So this is a pretty good sample, a very, very good indicator, or something we can plan to exploit to have a pretty good idea about the initial saturations of the native systems. In this particular case, we're looking at ultrasonic wave speeds, 500 kilohertz to 1 megahertz, and this is a function of the isotropic confining stress. Also, you see the effect of the angle as opposed to the fracture, as opposed to the effect of the angle from 0 to 45 to 90, and you can see at 0 again, we have the highest effect, and of course at 90 degrees we have the lowest effect. However, the important thing is that the peak wave at all scales, at all angles, is always shows higher velocities when the system is saturated as opposed to when it's dry. This is very, very consistent. Now, so we're looking now at the Young's modulus of elasticity and shear modulus as a function of isotropic confining stress. Again, what you see over here is that the saturated E modulus is always higher in the case of a wet system as opposed to a dry system. And as for the G, well, in this case, it makes absolutely no difference. It's pretty constant. We don't see any changes. And this persists in all cases of the different angles. Of course, for zero angle, we have the highest elastic modulus. In this case, again, it's between 800 hertz to 2.5 kilohertz. This is pretty high for field applications, but at least, this is, we are working with different frequencies too. Okay, now we're looking at Young's and shear attenuation as a function of isotropic confining stress. And again, you see, the same type of pattern. Now, the angle makes a difference. At 45, you see a very, very different, with the angle of the fracture. You see a very, very different behavior of the system. Of course, the saturated system has a very different behavior. The dry system is always significantly lower attenuation. This we already published, that we did in 2011. And compared to the ultrasonic tests, the resonant bar tests show rapid increases in the sample stiffness at low stresses below 5 megapascals. This may be attributed to relaxation of the fluid pressure within the sample because of the low frequency of the measurements. This does not occur at high frequencies. And the unexpectedly low Young's modulus and high attenuation for the saturated 45 degree core indicates that some of the hairline fractures were not fully saturated with water. That's the only explanation we have at this point. I think it's the final item, shale permeability. So for this one here, we have to use the inverse modeling. So our results were inverted using the ITAF code. This is the inverse TAF. In essence, we solved the inverse problem, which means in industry parlance, in petroleum engineering parlance, this is history matching, automatic history matching. So we have pressure decay permeameter, and well, this is a process. I don't think there's a point for us to discuss this in detail. Let's just say we get the data, and then we use inverse compressed modeling to estimate permeability, porosity, and the clinker parameter. What you see is an excellent on the left and less than excellent on the right fit between measured and computed pressure decay curves based on the estimated permeability and changes in the sample resulting from compaction, fluid distribution, possible desiccation, or system changes may affect sequential tests. In essence, what we're saying is that we've coupled our laboratory studies with our numerical simulation capabilities. Now we can derive very fast, almost automatically, properties such as the ones that I discussed earlier. Okay, permeability, porosity, clinker brick effect. Results. In the case of Montney, here's the permeability, clinker parameter, and porosity. Barnett 1, 2, and 3. This comes, and 3 reversed. This comes, courtesy of our U.S. friends in the industry. Some of them do not want to be fully acknowledged, so we'll just honor their requests. You see at the porosity we have to deal with anywhere between 6.5% for Montney to 1 to 2 to 3%, even lower for Barnett. And what's interesting is, these are pretty consistent. These are pretty consistent. The Barnett 1 and 2 and 3, they come from different sites probably within less than a mile from each other. And you can see it's pretty consistent in this case. Finally, gas absorption on shales. That's the last piece of laboratory work we did. The objective here is to quantify gas absorption on shale. We need to understand what is the absorption process, or if it is indeed the absorption process. Well, let's not spend any time on this because I've taken more time than I planned to. And discussion of the setup is not that important. You can see this from your, if you download this presentation. The typical response is the following. When we open the valve, we have gas moving from higher pressure to the low. We have a rapid filling of the available porosity. And finally, we have gradual absorption and adsorption into the shale. The thermal response, which is Joule-Thomson cooling, lasts only a few minutes. And what we found out is that we can probably ignore it if, for a laboratory test that lasts longer. In our cases, it lasts days. Okay? So, what do we see? Number one, look at the pressure. The pressure down here is up to about 1,500 psi. Pretty high pressure. This is methane. So what we're finding, actually quite consistently, is that there is no such thing as laminar absorption for methane. It's a pretty linear absorption. This is something we found with several types of cores. Okay? So in this case, this is both Montney and Barnett. I'm showing here only the Barnett. On the left, this is the methane. There is nothing but consistently a linear absorption, no matter what. On the right-hand side, what we say is that we ought to do this for both nitrogen and methane. So we have absorption by absorption, which is slowly filling the nanopores, rather than physisorption, which is the double layer basic idea of absorption. This could be a function of the samples we tested, as the high TOC blank showed highly adsorbent behavior. So it is possible. However, this does not change the fact that it's not a laminar process. It's a pretty straight linear process. Ethane is a different kettle of fish. What you can see is that we have curves that probably indicate capillary condensation. If you look at the shape of the curve, it begins to look like the typical laminar absorption. However, not exactly. What we see quite often is this kind of curvature over here. This could be reproduced, and we did that either by assuming or by examining the possibility of capillary condensation. The other way we can describe this or capture this is by treating the absorption not as an equilibrium process, but a kinetic process. There is a kinetic limitation to absorption. So absorption is a function of time too. So we have not completely unraveled the mystery, but this is what we see. Anyway, this was only a project. We've already done quite a bit and more than our fair share. So this being the case, this is where we stand right now. Very, very recent results. We'll continue looking into the subject. But one of the next steps we are planning is to look into larger hydrocarbon molecules like C3 and above. Want to see if, because in that case, the capillary condensation is going to be even more of an issue. So one of the reasons we have developed these capabilities to be able to look at the nanoscale is because we will be able to see the micro droplet of liquid ethane or methane or propane or whatever forming. And I think this covers the subject. Well, this covers the laboratory studies that we conducted within the F3G project at Berkeley. Okay. Thank you very much. So perhaps we can take a few seconds and then grab our coffee now. And then I will have to press on and impose your kindness by presenting our numerical simulation work.
Questions for George? What should we take from this that would affect us for other things like that? Everybody okay? Are you ready for your coffee? Go ahead, Sina.
Yes, sir.
Have you tried the influence of the sample geometry in geotechnical applications? We know that, for example, the modulus can be significantly increased.
You're absolutely right. To the extent possible, yes. In geomechanical studies, we tried the best we could. Keep in mind that we can only work with what we can get. Fortunately, some of the cores that we got from Montney, from Canada, were pretty large. We could do under coring, and it was pretty good. We were not that lucky with the Barnett Shale cores that we received from our friends over here. They were smaller in diameter, but we tried to overcome this by doing several tests with as many samples as possible. So I would tend to believe that they're quite consistent in their behavior. So it could be that there is a systematic error that is involved there, probably because of the same way of obtaining the sample, but within that constraint in mind, that limitation in mind, the results are pretty consistent.
So again, I don't really understand geophysics, but you said it's calculus wave. Can I detect?
Calculus.
Calculus wave. Can I detect?
Yes.
Hydraulic fractures.
Well, I'll tell you what. This is not part of our presentation here, but at the end of the presentation, if you're interested, I can show you the very recent laboratory studies that shows the way of how this can be tracked.
So
Yes, we can track it, yes. But in essence, you need to have a sensor downhole. So that basically means that you can do that anytime, before the beginning of production, or you can stop at any time and you have to stop production, and then you send out the signal, the acoustic wave, and get back the gravitational wave. Yes, you can monitor that.
So the detector needs to be in the well that you're.
Yes. The downside of this is that production has to stop. The upside of this is that you're not limited to the microseismic signature that comes within a few hours, that dies after a few hours. This is the hydraulic fracture. You can do that anytime you want. Yes, sir.
So, can the source and the receiver be in the same well?
Yes.
Okay.
The source actually is placed exactly where you did the hydraulic fracture. The idea is that you know exactly where you did where the stages are. So you send out this wave, and what you get back tells you the surface area, the distance, the extent, and also the aperture. So that's the idea. It has to be, the sensor can be in the well, but the acoustic wave is sent from the location where you know you did the hydraulic fracture, or close by. Because you know the initiation of the fracture, right? It's something you control. So in essence, this involves quite a bit of inverse modeling, because you get a signal back. From this, using inverse modeling, using history matching, you have to, based on the angle of the shifting, based on the frequency, based on the magnitude, all of these things, you can detect several things, like as I told you, the distance, the surface area, the aperture, the roughness. So it's not a single process. So in essence, what you want to do is make it as massively redundant as possible, and then based on that, come up with results. The basic idea is, and I'll have to say that, do not expect this to be a magic bullet. But if you combine this with microseismic data and possibly gamma ray type of work or anything else, you can more or less reduce the uncertainties about the fracture characteristics. Okay? It will never be a silver bullet which will give you all the answers, but it will be another technique that can help you reduce uncertainties. Especially because whether you like it or not, you rely on reverse modeling. And in these systems, as anybody but the worst liar or the most, let's say, frenzied numerical modeler will tell you, Mother Nature is not a deterministic system. You can have more than one solution, so approximate solution to the same problem. No uniqueness will kill you. So you use one technique to constrain the results you get from another. Any other questions? So when am I supposed to do my study, my presentation on the numerical modeling? What time do I begin?
Well, you're started in 15 minutes, so we're back on schedule. We'll take a break now.
Okay.
And that'll put you right starting at 14:30.
Perfect.
And again, we're exactly on schedule, taking the coffee break now. For our visitors who are uncomfortable in our third floor restroom, we have a really nice restroom on the 9th floor. Not that you would be uncomfortable, but midday students, there's probably been 1,000 of them in there. So.
I've got a theoretical question for you, George.
If I know the answer, Bob, it's all yours.
All right. So, with this type of absorption type model, you see differences between nitrogen, methane, and methane?
Yes.
What do you think the delta permeability curve would look like for non-wetting phase and wetting phase in this type of system? The reason why I ask is because I've seen a theoretical model where they used Purcell's bundle capillaries model. They actually ended up with a convex non-wetting phase delta perm curve. When anything with micro-RC range on up, it was all convex. I mean, the delta perm curves are the convex version. But in the bundle capillaries model that I've seen, in this Numerical type rock, they're actually using like a Purcell type model and they're getting convex up.
Well, I have to tell you something, Bobby. The honest answer is I do not know.
I don't know either.
I mean, it's
asking you.
well, I can come up with a gut feeling, but I have to tell you that my gut feeling has been proved wrong so many times in a shale, especially from I'm talking about what I expected, what I saw in laboratory studies, that I prefer not to venture any guess because I would probably perjure myself. I don't know, and until I do the research, I will not know. So I'll tell you what, though, if we send you a nice proposal, will you fancy to look into this?
We'll see.
Okay.
So why did you stop at 1,400 pounds on the absorption method?
Ah, excellent question. Because above 1,400 pounds, you're dealing with very different health and safety issues. So that basically means you get the possibility of real explosions with combustible materials. And in essence, we had to manufacture a different type of containing vessel to be able to do this research for higher pressure. So we already got to that point. Okay. What can I say? We cannot go about, I mean, within up to 1,500, we get linear results, okay? But
It's PSI, right?
it's PSI. It is gauge. Okay? No, well, another 14 is not going to make any difference.
Back here, 15 PSI.
Kills gauge, but still. Okay. But again, we were, the difference in cost between what we did here and the one rated for up to 4,000 PSI, which is the next level, is a factor of 6. So they gave us quite a bit of money that, and put it this way, I mean, what you see over there is the results of a single project. And we're talking about 10 thesis and dissertations, 40 or 50 publications. Come on, we cannot do everything. We have to have Bobby Funders do the rest. Okay, Bobby? He's claiming he's not listening.
When it comes to hand out money, I'm sure he's not.
Yeah.
So I didn't, which company are you with? Oh, you're with What's that?
Quebec has always been.
I'm beginning to agree with you.
Well,
I don't
No,
know.
hold on a second.
I don't know if you can't tell anything.
No, let me
You
qualify
can't-
this. An excellent
you
point.
cannot tell everything that Microsoft.
Oh, sorry. Yeah, I didn't know that.
well, I mean, the problem
Much better.
is,
Leave it like this.
some of the companies have oversold it. And this thing that you mentioned about the energy that's released during the microseismic and the energy we put in with fracturing, I mean, I think that's been, I thought that was generally accepted years ago, that we knew that, that most of the hydraulic activity is aseismic, at least aseismic within the frequency range we're looking at, and that there's no way you can extract the hydraulic fracture structure from microseismic data. Check that box. No, we could argue about that, but I'll say probably not, at least in the near future. Okay, but the thing I will argue about this is that there is some evidence, okay, that in many cases the microseismic tells us where the hydraulic fracture is located.
Absolutely. Actually, let me qualify my earlier comment. It was not addressing the theoretical ability to describe fractures or give information about fractures, which I think it can. It was more addressed to the reality of the field reality. Because unless you have the proper location of the sensors, and unless you do the corporate version, and unless you have sufficient number of sensors, in essence you get some data, but there's a question of the usefulness.
But this is true of regular science. If you don't design the program right,
Exactly.
you get nothing.
Exactly. And because seismic is microseismic is pretty expensive, what they do is they use sensors, they don't put it in the right places. That may
There's limitations for sure.
Yeah,
Yeah.
of course.
It's just that.
I was addressing this issue, not the theoretical. Yes, you get some information.
But I mean, I think that even with the single observation well data, that when you, I guess
You were talking about the surface side.
Yes. That's surface.
surface microscope. Well, I'm talking about downhole microscope.
There is that too.
Yeah, I mean, there's always issues with location, wall bias, and all that stuff.
Exactly.
But yeah, I guess that I was trying to balance the what we don't know with what we might be able to, what we routinely think we get. I mean, when you look at a lot of the microseismic data, some of it is quite simple in that you frac and the microseisms appear where the perforations are. And as you march down the horizontal well, the microseisms move. I mean, it's not because someone's painting them there. I mean, that's what the signal says.
Absolutely.
And the heights many times and things like so. Yeah, so that's the only thing I was going to couch it with is that right now, it seems like there's a lot of cases where the microseisms tell us in general where the frac is located within.
I don't dispute it.
Within error.
I don't dispute it.
Yeah.
I don't dispute it. But what I'm also saying is that, and let me tell you about a case we have where we looked
Yeah, well, well, that's got to be surface data.
It was.
Because usually trucks driving by will not affect gallons.
Yes,
Yeah.
but still,
Oh, yeah.
this guy's.
But that's the case with any side. Doesn't have to be.
Exactly.
Yeah,
You don't do it right, you don't get it.
yeah, surface activity.
That's
Kill it.
with any data.
Yeah, no, and there's examples, and there's where you don't see much microseismic activity, and you know you pump, you know what you pump is.
You know the fracture.
Yeah, oh yeah, we know. There's no doubt about that. Yeah, you frac.
Actually, some of the work that we didn't show today, because Mark did not include in this presentation, was he gave this case over here, which he has correlated to the amount of clay in the system.
Yeah. Well, I mean, I think that's I understand.
You're talking to someone who lives in the Bay Area, everything's a lot.
Yeah. Well, then I guess that was kind of my point, is that the overselling is we can take, you see people drawing fracture structures, you see all this crazy crap that just isn't the microscope. But, you know, I'll argue that I think I can take microseismic data and use it as a guideline for, you know, for trying to fit a hydraulic fracture propagation model to, you know, to that, you know, for the frac to be basically in that microseismic ball. Okay, well, maybe it's got close to that height, maybe it's got extended out this far. There's something along those lines that it's a guideline. You know, in a vacuum, you know, microseismic is not going to tell you everything. But if we didn't have it, I don't know. I mean, I'm going to be struggling even more to try to figure out what my frac can make. And where, when, you know, so that's the problem.
It's been 20-some odd years ago. There was a guy there that ended up building one 3D fracture model. He also built it to water hammer. Water fracture was sold.
Yes, wholesale. That's initially with a water hammer stuff. He patented it. He has a Safari? No. Okay. Yeah. But to the water hammer. Yeah. It's just that we never figured out how to never get what you want to get is fracture. What we really figured out we could use it for is to figure out where the frac was over and close. So we tried to use this way to corroborate closure fix from mini frac data. Because you would see, basically, when the frac was open, you got a certain type of reflection, positive or negative, I can't remember. And then when the frac was closed, you got a reverse polarity of that. So that was pretty easy, but the different dimensions, it was never anything that we figured out.
Well, this guy actually had come with this geometry model.
Yeah.
In order to like it.
Well, it's the only understand what the geometry model is how the geometry model itself helps. I can see that you, if you try to model what the reflections would look like, but it's, yeah.
Show you. One of them was coming up with something looks like that we normally see with real permeability like this. And then over there, see the rocks over here. This is like a Bernine type model.
Okay. I hear what you're saying.
But if you use personality model, which doesn't need the direction of north west, the non-wetting phase, you get a convex upward curve. That's what I was curious about, as you see it.
What's happening is that there is technique that we use.
I'm guaranteeing you. I really am.
Capillary, if you get the capillary pressure, it's a function of the.
Yes.
Maybe you could use one of these empirical models. For the wedding phase, you can use either one. They both give you a good match on the wedding phase. This is personnel. One was capillary forms. Different shapes. This one is the correct one for microdorsal.
That quantifies we have input on something like that, which I'm pretty sure SOD would love to fund, right? That'd be nice.
Maybe.
Send us some money, right? Okay, we're hurting you. We're not that hurting, but you know, come on, be nice to us.
You guys got a few spare millions. You guys.
Oh.
I don't know. I wouldn't expect you to be funding research. That's not a good return on your investment. What would they need?
Το βάλουμε full screen επειδή δεν φαινόταν την προηγούμενη φορά. Θα τα cancel.
Ποιο? Μιλάς
Ναι, στη μέση το presentation.
Φελή.
Δεν μπορείς να το κάνεις στο chat.
My eyes are this very difficult time. They cannot figure out which way to go. I cannot see far, I cannot see close.
That's what they have multifocal lenses for, right?
That's for old people though, so I refuse to wear them. Allow me my illusions, right?
Yeah, okay, go ahead.
Makes sense? Okay, where's my buddy? Mas.
He's back. He's up on the 9th floor visiting his fancy bathroom. I've never heard as many bathroom advertisements in one meeting in my life.
Well,
I gotta go up there just to see what that thing's like.
here's the deal. The higher you go up, the lower the frequency of usage of the bathroom by students.
Ah, okay.
So,
Yeah.
one of the better places to go is the 5th floor where the suits are.
Ah.
The department head is. So chances are it will not be frequented by many students.
So are you saying students are a lower life form? Is that what the...
Me?
Grad students.
No.
No, he's saying there's a lot of lower life forms living in the student's bathroom.
Ah, okay, yes, okay, there we go.
It's the opposite, actually. It's not the opposite. It's a different perspective. It is like the self-importance of the suits is a little bit more demanding than that of the students. Okay. Okay.
It says the man in the coat.
2:30. So we'll discuss. We'll discuss our numerical simulation capabilities. Keep in mind that most of the work that I described in here, which involves the real gas water and real gas brine of the TAP class code, and the next code that my colleague Jikun Kim will discuss, which is basically coupled flow, this part, coupling this to a full geomechanics model, and also coupled to a geophysical model. These are codes that were developed in Berkeley, and some of them with friends, with the help of, in terms of developing data, friends with the help of the students here at Texas A&M. And these are available to the public. Actually, they will be released officially to the public in a month or so. Keep in mind that when we say release it to the public, we do not mean we give them executable. Even the source code is available to everybody. Basic idea is that whatever we developed was done with the support of the U.S. taxpayer, so it is released to everybody. Okay? Now, what I'm discussing over here is the real gas water and real gas brine options for the TAF Plus code, and this is for the simulation of coupled fluid and heat flow. I'm seeing here tight and shale gas systems. However, the reality is much different, wider. It can be used to describe any gas system. What I mean by any gas system is that if you're going to do, God forbid, for some of you, CO2 sequestration or CBM or any other kind of study that involves gases, this is entirely applicable. You can use for any regular gas reservoir with absolutely no problem. But mainly the reason we discuss here, the reason we discuss it here is because we have built-in capabilities that can address the specificities and the particularities of tight gas systems and shale gas systems. Okay, we'll discuss the background, we'll give a short code description, then we have some validation examples and some application examples. And as I said, within a month, we're in the process of finishing the user's manual. Within a month or so, this will be available from Berkeley. Just go to the website and you can find it, get it from there. And the cost is really minimal. So this is a member of the TUF Plus family of codes. The TUF family is a family of codes that was developed in Berkeley. Now they're being used by about 400 organizations in 65 plus countries. It is 1495 of 2003, which basically means that it's not very different from C anymore. It's object-oriented programming, and it has modular structure for ease of expansion and maximum traceability. We use this for some of the most difficult problems. So the TUF plus real gas water. This can be used for conventional tight or shale gas situations. We have dry and wet systems respectively, and here you simulate water up to 11 gas components. It's known as isothermal. So the minimum number of equations in this would be about 3. The maximum number would be about 13 equations. In addition to this, there is a very recent, actually it's like last month or so, version of this code. It's the real gas brine. That's what the B stands for. It's the same thing as TUF plus real gas water, but here we have salt. What does the salt do? Two things. Number one, we have one more component. In addition to this, we have the possibility of one more phase, and that is precipitation of salt, which is not a trivial issue. This precipitation of halide, that's the salt, what the salt precipitate is called, because the salt can change significantly the properties of the water. It can change significantly the dissolution of gas into the water, and it can affect tremendously the porosity and permeability if we have the beginning of precipitation near the well or near the fracture, which is by no means impossible, as we're finding out. Fundamental equations. Okay, I'm sorry if I bore you, but I have to go through this. What you see up there, this animal is an integral differential equation, basically saying nothing more that the change in the accumulation is equal to the change of the flows or the flatness of the boundaries of the controlled volume, plus the effects of heat of sources and sinks. This applies to both mass components and applies to heat components. In terms of mass accumulation, this is a simplified equation. Actually, this is a summary equation that involves the contribution of the components in the phase over here. Kappa are the components, and the components are, mainly the gases and the water, and the beta are the phases. The phases are the IQs and gases. In addition to this, we have this term over here, which corresponds to nothing more than the sorbed gas of the system. This applies only to shales, not even the tight gases. The sorption. Well, we have several fundamental equations. What you see over here is the typical Langmuir equation. At the top, you see the equilibrium Langmuir, and below this, you see a kinetic, because we see evidence from our laboratory studies that some of these sorption equations are kinetic. They are not equilibrium. This applies to a single component. You may have multi-component, in which case this is what the sorption equations look like. However, in addition to this, to be on the safe side, the code allows for linear sorption, kinetic in equilibrium, and also Freundly absorption, also kinetic in equilibrium. So, in short, there is no possibility of having any type, any form of sorption equation which we cannot describe one way or the other. Heat accumulation. We have to account for the contribution of the rock, and then, of course, the internal energy of the fluids, plus the internal energy that is associated with the sorbed gas. In terms of flow, what you see over here is in essence, the component flow is equal to the sum of the contributions of the different components in the phase fluxes. And here, this is the typical, well-known basis of our work in porous media, and this is the Darcy's law. Does it apply? Probably not. Actually, what we're finding out is that in tight media or under certain conditions, even regular media, this does not apply. So what do we have in the case of gas flow in tight media? We have non-Darcy flow by the introduction of this parameter over there. This is the Klinkenberg parameter. In addition to this, if we have more than one component, there is this J component up there, and that is the diffusive type of fluxes. And of course, we all know that diffusive fluxes, they are caused by variations in composition as opposed to variations in pressure, which causes the advection the advective part of the flow. Now, the additional thing I want to indicate up there is that this is good and great whenever we're dealing with a single component, okay? Now, what you see over there is that when we have a system which is very, very tight, and so tight that the Brownian motion is affected by the fact that the pore is extremely small, in that case, this Klinkenberg parameter can be obtained from the Knudsen diffusion analysis, and this is the big we get from this study. And what we show over here is how this is computed. Now, this one here, this lambda is the mean travel path of a particular molecule. So, in essence, what you see over here is the fact that this becomes a very important part of the flow. And as we discussed earlier, it is, especially for lower pressures, this B can be so large that the majority of the flow, especially in the vicinity of the fracture inside the matrix, the majority of the flow is diffusion-based. This is all accounted for. However, if you have a multi-component system, you have now binary diffusion. One component diffusing into the next. And in this case, we have to use the dusty gas model that was developed by Steve Webb and Carsten Pruss. And that was 2003, I think. And this is probably the most advanced model there is on this case. And here, in addition to everything else now, you have to account for binary diffusion plus Knudsen diffusion. This more or less captures this is the state of the art. There's nothing more advanced on the subject, and this is what we already have in the code. Now, there are parts of the flow system, certainly in the case of large fractures, where we don't have Darcy flow. So in a fracture with very high permeability, you have non-Darcy flow. In that case, we have two options. One of these options is the Forkheimer equation. Roughly speaking, instead of the production of Q being as a function of delta P, the change in the pressure, now we have the Q being a function both of P and delta P and delta P squared. In essence, we have an additional term. It's a quadratic type of equation. So this is what you see over here, the velocity in that case. So we have the option now, if we have large fractures where we know the velocity is pretty high, to incorporate this in there. And that can have significant implications, especially if we do a non-isothermal process, because that creates Joule-Thomson cooling. So you can see things how you see that the gases cool very, very fast in the fracture. Also, you can have, if you have a regular reservoir, this can happen right next to the well in the case of a very permeable reservoir. In addition to the Forkheimer, we also have the Barré-Tourvé model built into the system, so it is an option. Now, heat flow, we account for the first part over there is conduction. Then we even account, of course, advection is the last part. The mid part is radiation, just in case. Well, there are some cases where radiation is important, probably not in our case. Most of the cases we deal with over here. We deal with the sources and sinks in all possible ways. The water properties come from the steam table, so there's no such thing as you can say, I'm going to give this property to water. You cannot touch that. These are the most updated water properties as available from steam tables. And in terms of real gas properties, we have three options there, either the Redlich-Kwong, the Soave-Redlich-Kwong, or the Peng-Robinson equation. We have a library with 11 component gases. And what is happening now is to address the point, I think it was Bobby made this earlier. And we're in the process of investigating the PVT properties in very tight media. When this becomes available, we will incorporate this in there. Okay? However, at this point, we have the kind of bulk behavior. We have not quantified it yet. We know it's significant. And it's going to be even more interesting, especially if we expect, if as we expect, we will see the creation of micro droplets of liquid hydrocarbons in the pores. Okay, that will change significantly.
Does mist have brine properties, or when you put the salt in?
When you put the way it is right now, the properties of the salt, the effect of the salt is fully accounted for. Okay, now you're raising a very interesting issue. We are in the process of developing the PVT. Initially, it's just water and gas or pure gas. Later on, we'll see if the effect of salt is anything to worry about.
And so the PVT of the hydrocarbon phase is always gas, or can it have condensate?
It can have condensate, yes. See, what's happening is Peng Robinson and Soad Redlich-Kwong, they allow you to do go seamlessly from liquid to gas. Okay, it's not the problem. The older one, the Redlich-Kwong, does not allow this. So this is possible. However, what's happening is that in that case, the thermodynamic property, actually maybe mainly the enthalpy is not very accurate. So for this case, what we do is when we have this happening, we switch from the continuous cubic equation to tables or specific data. For example, we have the properties of CO2 there. CO2 is one of the worst materials to work with in terms of properties. If there was any justice, CO2 would have been a liquid, but it isn't. And so you have different enthalpy tables for that, and that's what we do for the other gases. So this is fully accounted for right now. But when this comes into play, things may change significantly. Okay? We don't have that yet. Actually, nobody has that yet. We have some simplified geomechanics built in. Of course, we have the typical porosity dependence on pressure and temperature deviations. However, in addition to this, we have the model that was by Radquist and Zhang that describes the permeability relationship to changes in porosity. This is very good. We've seen this being effective over a very wide range of material, from unlithified and unconsolidated sands all the way to some of the strongest, the tightest, the rocks you can find, like welded tuff. So this is pretty good. So additional physics, we have gas solution to liquid physics. Anyway, I think we have incorporated most of the properties that are of the system, the physics that are available, that are known to us right now. Keep in mind that this is a research code. That means that the important thing for us is to make sure that we account for all the properties, all the known physics of the system. That may come at the expense of speed. We do not plan to use this and give our director or somebody results by tomorrow if it's a very large system, because the execution may take a day and a half, especially if we have 2-3 million grid loops or 3 million equations. However, it will take far more time analyzing the results. So keep in mind, it's a research code. We'll give you all the information you need. We do not discount anything. We do not leave any processes out. We want to be able to analyze the relative importance of these processes. So what you see over here is the way we describe fractures. We have two different ways of describing fractures. One of them is a so-called discrete fracture. We described the fracture, individual fracture, as a subdomain, its own porosity, permeability, relative permeability, everything else. For example, if we have hydraulic fractures, in most cases, some of the studies that we discussed up to now, what we do is we make sure that we describe the fracture, the geometry, the properties of the fracture, and that is, as I told you, a subdomain. There is another technique, and that is called MINC. And that, in essence, allows you to subdivide the domain in two different pieces. There is a fracture subdomain, and there is a matrix subdomain. The simplest realization of this is the double porosity model, okay, where all the flows of the fractures, and then the matrix just feeds the fractures. However, then this is just the simplest one of the possibilities. Well, we have now situations where we have three different layers of fractures. You know, large fractures, thin fractures, ultra thin fractures, micro fractures, and then we have 3 or 4 different types of matrices. And you can decide the interactions. It's up to you to decide what the interactions are. So you can have, generally speaking, we have the option of having matrix to matrix, matrix to fracture, fracture to fracture at any level. So this is the MINC technique, was developed a long time ago in, relatively speaking, Berkeley. This is what they used to simulate the radionuclide transport through Yucca Mountain, the fracture rocks of Yucca Mountain. And this has been proven, at least in several field tests that we have conducted. So I'll go very, very fast over this. In essence, I'm just describing here the capabilities of the code or the features of the code. We have name list-based data, which basically means you read the inputs like English, so you cannot get lost over there. Dynamic memory allocation, you can have on-the-fly changes. Usually Fortran does not allow you to change things once you begin running. Here you can do that. Built-in initialization, so in essence you can give the data and say, okay, find me the initial conditions. Of course, you have to give it the correct data. And initialization flexibility, time variable boundary conditions, all of these things. So, okay, I'm gonna give you an idea of what some of the inputs look like. So in essence, you can read this in again, it reads in English, so you can never get lost in this one here. And the good thing about these name lists is that you can have the properties or the variables that you read in any order. That is very, very significant, because if you have formatted Fortran, it can kill you. Some additional features that of the system. For example, what you see here is the equilibration block. You have this in there, you provide the data, and then the code will run by itself and stop until when it finds the initial steady state, which will be your initial conditions. So if you're going to do gravity and thermal equilibration, this is what you need to do. It's done automatically for you. Now, validation examples. This is good and great, but, well, how does this compare to, you know, analytical solutions, real-life solutions, anything? So, radial gas flow in a cylindrical reservoir. This is the problem which my old friend Mike Frame developed in 1986 with Wattenberger. This is the year I graduated, guys. Oh my God. Where did the time go? So, you see the matrix permeability, all of these guys, cylindrical reservoir. So we're checking out whether this will work well in a gas system. So what you see here is a comparison between the analytical solution and the numerical solution. Keep in mind, the numerical solution is always more accurate because we're able to account for the complete nonlinearity of the system. And in analytical solution, we have to make some assumptions, which usually affect the accuracy of the accurate representation of the system. The next one, okay, so we can do gas. How about being able to do water? So for this, we use the analytical solution of somebody I barely know, and that's Tom Blassingame. And here is the properties of the system we investigated. And for this case, here is the comparison between the analytical solution and the numerical solution. So we're quite happy. So we can do water, and we can do gas in a regular porous medium. So what happens if we have a tight gas reservoir with a vertical well intersecting the vertical fracture plane? That's beginning to get more interesting. Fortunately, there is an analytical solution of Cinco-Ley, 1978, and then Cossiot in 2012. And here, this is what you see in terms of point cloud pressure distribution. But this is distribution we see, the contour plot of the pressure distribution around the system. And this is the comparison between the analytical solution and the numerical solution for two vastly different sets of properties. So we are pretty happy. We have a very good solution over here.
Does your code figure out the grading?
No, sorry. The grading is development of the grid is something you have to do. So it cannot be an automated process. Sorry. In addition to this, because this is fully implicit, and here's the Jacobian, we cannot have adaptive gridding, because the basis of this solution is near perfect mass balance, 10 to the minus 5%, that's what we work with. So this being the case, you cannot just split grid blocks because you cannot find perfect mass balance after that. So it's something you got to do. Okay. Then, well, okay, water and root fracture system. This is a dual porosity model. Unfortunately, the person I asked to do that was trying to get out of Berkeley because he had just gotten a job with the industry where the compensation was much, much higher. So this being the case, he only used about, what, 30 grid blocks or even fewer. So I did not give it a, it is a pretty good match, but I expect him to use a finer grid. But anyway, this is fine still. And finally, there is an analytical solution of flow of gas in a system using the Klinkenberg, the Klinkenberg parameter. So this is a solution that Hu and Carsten Proust developed in 1988. And what you see over here is a comparison between the solution, the numerical solution, the analytical solution. So we're pretty happy after that. We can never say that a code is perfect, but we have indication that it works quite well. So, problem A1. This is the problem that Tom discussed earlier. What we're doing over here is we have a gas production from a shale gas reservoir using a horizontal well. This system subdomain is the matrix and natural fractures. This is the S1 type. And this is what it looks like in this case. We have the stencil. Stencil is the minimum repeatable element. What Tom said, forgot to say, because he had too much material, is that the work of Femi showed that this is accurate compared to a full 3D system simulation. I mean, instead of simulating just one stencil, simulating the entire wellbore system plus the boundaries with the same level of accuracy, this is accurate about 3,000 years. That's what Femi showed.
They both ran some tests.
Yes.
And so if anybody was curious, they did validate the stencil concept.
So,
and it cut the computational time
right.
by.
We use the stencil. Let me show you what a bit better representation over here. This is what the stencil looks like, and this is accurate to 3,000 years. So he had to compare this to a simulation of the entire three-dimensional system, a system which was supposed to be like 4,500 feet long, and plus boundaries and everything. This, when simulated as a full system, it was close to 10 million equations, and they show that there is basically practically no difference until about 3,000 years. So we felt good after that. That's what Femi did. He burned I don't know how many thousands of hours of supercomputer time. So, problem class 1, problem A1. What you see is we have the horizontal well, we have the stress release fractures over here, hydraulic fracture, the rest of the system is like that. Similarly for vertical wells, and you saw that. In this case, it's a 3D system, millimeter or sub-millimeter level of discretization near the fracture and the wellbore. We have about 800,000 elements, and in essence, what we see is this type of QD versus TD, dimensionless rate versus dimensionless time. So we can do that pretty effectively. And you see the very, very high steep pressure gradients near the fracture and the wellbore, which is exactly what we were expecting to see. Additional sound sensitivity analysis, what you see here on the left is the effect of fracture conductivity. So of course, the more conductive the fracture, the more we produce. And what you see over here is the effect of fracture spacing. Initially, it doesn't make very much difference, but of course, later on, it makes quite a bit of difference. Then we try to investigate the effects of different fracture types. In one case, we have just the fracture, the main fracture, and the matrix. Then we have the fracture induced during stimulation. So there are some primary. This is the hydraulic fracture over here. Then we can have secondary fractures, which we know develop almost perpendicular to the vertical hydraulic fracture. And finally, we have some other stress release fractures. So we try to see the effects of different fracture on the behavior. So that's what you see over here. This is the type 2. In addition to the vertical fracture, now we have these stress release fractures. Then we have type 3. That is basically the vertical fractures and a whole bunch of native fractures. This is a possibility. And number 4 is type 4 is everything in the kitchen sink. So what happens in this case? What happens in this case is we have a very different behavior. The reference case, type 1, is the red curve, and you can see that the other types of fracture systems give you a very different behavior. This is log-log, so we're talking about an order of magnitude more gas rate, higher gas rate initially. So translation, we need to be able to describe the fracture system because otherwise we misinterpret the real mechanism of gas production and what is happening in the system. Because if you have a behavior like the one described by the green curve, which is type 4, and you try to describe this using the behavior of type 1, what's going to happen is you're going to have a curve fitting process which may be able to capture some of the actual behavior, but is entirely wrong in terms of overall behavior because it describes different physics. So the fracture system is incredibly important. A3, this is a different, I'm almost out of time. This is a situation which Tom has already described. Instead of having just one gas, we have now 6 different gases. This is the gas composition. You see here the different Langmuir storage that we have associated with this type of problem over here. And we try to see what is happening in this case. In terms of the gas fractionization, this is a kind of distillation process. Tom has already described this. We have 800,000 elements, which if you multiply this by 7, I'll give you 5.6 million equations. This is what we're solving over here. And what's happening over here is that we see what Tom has described already. We have the times, the transition times from linear flow to compound linear, and then here is the combined linear. We have, in essence, the situation where at these points where we have a change in the flow pattern, we have the inflection points in all these curves. The additional thing to see is that there is a difference in the composition which evolves over time. And this is some, in essence, we confirmed actually Matt Freeman did this work using this code. He developed part of this. So finally, this is a problem which is very recent. This is the evaluation of the potential environmental impact of hydraulic fracturing of shallow groundwater. We have Berkeley, the only project that evaluates the impact of hydraulic fracturing of groundwater. This is our work. We have to report it. It used to be reported to Congress because this is what Congress demanded. So I'm not going to get into specifics because I cannot do that before the report is released to Congress first. But what you see over here, we investigated different composition, different possibilities. A variation in shale permeability from micro-Darcy to nano-Darcy, aquifer permeability, connected fractured fault permeability. And in this case, the basic assumption is that we have the shale reservoir, we have the shallow aquifer, and they are connected somehow. It could be that there is, a continuous fracture that goes from the shale to the aquifer. There could be that there is a fracture that goes partway up and then finds a dead end, dormant fault or fracture, and then there is connection. It could be that intercepts an abandoned well, which we know nothing about. Keep in mind, we make no assumptions about whether this permeable pathway exists. We consider it a given. And then we try to see what's going to happen to gas in this case, what's going to happen to the water. Do we expect to see a problem? So, and we have different protection strategies. One, we have the water well producing at a constant rate, and then we have the shale gas, the gas well producing at a constant bottom hole pressure, half the discovery pressure. Or we can have only the shale gas well producing, we can have only the water well producing, or no production from either formation. So, okay, well, I'm going to show you one result, but do not feel that I'm giving you the whole story, because when the shale gas is producing, there's basically no problem. When there is no production with formation, we don't see much of a problem either. This is the worst possible case scenario, and under these conditions, this is what the system looks like over here. And this is the three-dimensional grid that we have developed for this. It's extremely complicated. We had to use Voronoi grids for this. It's several 100,000 elements. Non-isothermal, because the temperature between this point and the shallow aquifer can be very significant, so we cannot assume it's isothermal. And this is an example, nothing more than an example. Here, what we have is a high permeability fracture connecting the reservoir to the aquifer, the high shallow aquifer. So this is what happens at the base of the top of the shale. So this is the gas coming up. Okay, this is what is shown at the bottom of the aquifer, and this is what shows up at the well. This is 10 to the minus 5, so it's basically below the solution, the solubility limit of methane. So it's very, very little problem in this case. Keep in mind the permeability of the fracture is very, very high. We have 3,000 darcies. If the permeability of the fracture is 3 darcies, then we see a little bit of gas shale that reach the top of the we'll see a bit of gas reaching the top of the shale, but nothing shows at the bottom of the aquifer, and nothing shows at the well. It's background. Okay? Generally speaking, it is safe, and I did say that. Okay, if we have now connecting the aquifer, sorry, the shale reservoir to the penetrating well, connecting the shale reservoir to the aquifer through an abandoned well, an offset well. So what you see over here is are the rates of gas evolution, gas appearance at the bottom of the aquifer, top of the shale, and produced at the well. So what you see over here, right axis, we are about 10 to the minus, a bit over 10 to the minus 5, like 6 times 10 to the minus 5. So it's again below the solubility limit. This is what shows up at the well. But what you see happen is boom, this gas coming up. Well, this is the initial gas in the fracture and just goes up all the way. By the way, if we assume that initially we have nothing but water in the fracture, we will never see any gas coming out. End of story. Not the problem. And what you see happening over here is what we see what happens at the base of the aquifer for different permeabilities of this abandoned well system. If we have 3,000 darcies, you have this boom, gas coming out. If it's 3 darcies, we have this situation, 3 millidarcies or 3 nanodarcies in essence. Now these are basically permeabilities. You assume that the cement of the abandoned well is intact, so there's, in that case, nothing happens. And with this, I'm sorry, I apologize, I went over time. I'd like to conclude. Sorry for overstaying my welcome. If you have any quick questions, please. Otherwise, my friend and colleague, Ji-Hoon Kim, who, by the way, is abandoning us. He's absconding to join Texas A&M in August. He will be giving you the discussion for the
Sorry, you win, we lose. Anything else?
No, you win. Yes, I lost. All right. So the Ji-Hoon will be discussing the continuation of this effort, coupling this is coupled flow and thermal processes, and Ji-Hoon couple this with geomechanics and then geophysics, which involve both seismic and EM. And in essence, you have the title of this project was F3G, flow, coupled flow, geomechanics, geophysics, geochemistry. So I showed you the flow. Thermal was not even discussed, but we already have it. And Ji-Hoon is going to take care of the rest of the coupled processes.
We are a few minutes ahead, but your choice. You can be like George and expand and fill it, but we're okay. You've got about an hour.
Well, the things that expand to fill the volume available to them are gases. What are you implying?
Nothing. Your vaporness.
You're okay, you got it. And the way these work, who's got the other one of these?
Oh, I'm wearing it, sorry.
Okay. Well, the way it works, the easiest thing to do is just to clip it on your pocket, like that.
Thank you.
Got to recharge it. All right, you're in charge. We don't have a clicker, just from this way.
So do I start now?
Yep, you're ready to go.
Okay, in this talk, I'll describe the integrated coupled flow, geomechanics, and geophysical simulator, and then I'll show you some examples of the application for shale gas reservoirs. Well, The shale gas reservoirs exhibit extremely low permeability, so usually gas is produced from the naturally fractured or artificially fractured reservoir by using hydraulic fracturing. But the fracture is highly deformable, and for volume and permeability are closely related to the geomechanics, so we need a rigorous modeling in coupled flow and geomechanics. The outline of my talk is as follows. First, I'll show you how the geomechanics simulator, called the RockMag, is coupled to the flow simulator, Top Plus code. And then I'll show you some numerical examples. For example, hydraulic fracturing propagation and electromagnetic geophysical simulation and the modeling of the micro-earthquake and the failure analysis along the vertical well in the case of the incomplete cementing. And lastly, I'll show you some failure analysis during gas production. Okay.
Better?
Oh yeah, thank you. The RockMag is the geomechanics simulator. It's developed in the Lawrence Berkeley National Lab. It is written in Fortran 95, and we employ the finite element method. For plasticity modeling, we have two models. We use the Montney model for shear failure, and we use the concept of the node splitting for tensile failure. There are two versions for the coupled flow and geomechanics. One is the full 3D version, but in most cases, plane strain 2D geomechanics is useful, so we have another version for computational efficiency. And then the RockMag geomechanics simulator is sequentially coupled the top family code. So let me briefly overview the input files of the RockMag. The first file contains the general control parameters such as the number of the unknowns and number of the node and the properties of the rock material and the output of the monitoring points. The second file contains the connectivity matrix of the node and the element in the context of the finite element method, the coordinates of the node, and initial total stress and boundary condition for geomechanics. Third file contains the connectivity between the flow and geomechanics, and initial pressure and saturation for geomechanics for initial time. And we also assign a material index, rock material index for geomechanics. Also, in the case of the multiple continuum approach, we include a fourth file. There are two approaches to make a coupled simulator. One is the fully coupled, also called the monolithic scheme. The other scheme is called the sequential method. Although fully coupled method provides usually numerical, unconditional numerical stability for the well-posed problem, it is expensive in terms of the code management effort and computational cost. But when we use the sequential method, we can make use of the existing robust simulator. Here, what we need to do is to construct interface code only. But when we use the sequential method, there are issues we need to deal with: numerical stability and accuracy. From the recent study, the fixed stress sequential method for coupled flow and geomechanics provide numerical unconditional stability and high accuracy, so we used that sequential scheme. When we couple the flow and geomechanics simulator, we may have a different space discretization scheme. For the flow, finite body method is used, whereas the finite element method is used for geomechanics. So we have a mixed formulation. In other words, displacement, geomechanics unknowns, are located at a corner point, whereas flow unknowns, pressure or saturation, are located at the cell center. And this mixed formulation can also provide numerical stability in space. For the time discretization, we follow the time discretization for of the flow problem, which is the backward over method. We have the following solution procedures. First, we solve the flow problem. Then we get the solution, pressure and saturation. Then we solve the geomechanics. Then we get the solution of the geomechanics, displacement, strain, and failure status. Then we update the porosity and permeability or for compressibility in the case of the elastoplasticity. For the geophysical modeling, from the solution of the flow and geomechanics, we can simulate microscopic and electromagnetic geophysical responses. Let's look at the coupling term in more detail. The first of the porosity function, the first two terms is usually used in the reservoir simulation. This first term is related to the pore compressibility, and second term is related to thermal expansivity. And PTs are pressure and temperature respectively. So the third term comes from the geomechanics, which is the correction term. For the permeability, we use the cubic load. Here, omega is the fracture opening. For shear failure, we assign a higher permeability than the intrinsic shale gas reservoir permeability. So, in the flow, we have a coupling term like from the geomechanics, like here and or here, depending on the failure status. For geomechanics, we have the following stress-strain relationship. The total stress sigma is expressed in terms of the epsilon, strain, and pressure, and temperature. So this term, first term is called also effective stress. And these two terms come from the flow problem, flow solution. So flow and geomechanics are coupled each other. To model shear failure, we use the Montney model. Here we used conventional return mapping algorithm. It means that first, we predict some trial stress, and then if that stress is over the failure line, actually over the failure envelope, then we project that trial stress onto the failure envelope. So the nonlinearity of the geomechanics lies in the knowledge of the geomechanics is in the geomechanical model line. On the other hand, for modeling of the vertical tensile failure, we use the concept of the node splitting. Here is the node. The effective stress at that point satisfies the failure condition. We split the node. Then we have an internal boundary. But in the case of the vertical tensile fracturing, we can reduce the system in half, placing the internal boundary to the outer boundary. Then we can only change the boundary condition type. For example, from the Dirichlet boundary condition to the Neumann boundary condition. So the nonlinearity of the geomechanics is in the boundary condition. For the verification of the code, we introduced 4 test cases. First, we introduced the Mendel's problem. Horizontal axis is dimensionless time, and vertical axis is dimensionless pressure. And this hump is called the Mendel cryo effect. The second example is the fracture opening for the static fracture, and horizontal axis is fracture dimension, and vertical axis is a fracture opening. And also, we introduced 2 additional test cases for the viscosity dominant and toughness dominant fracture propagation. And vertical axis is the fracture length, and horizontal axis is dimensionless time. And as you can see, for the 4 test cases, numerical solution and analytical solutions are in good agreement. Then I'll show you some examples, numerical examples for fracture propagation during the hydraulic fracturing operations for vertical well and horizontal well, and followed by electromagnetic simulation and the modeling of the micro-earthquake. And also, we will investigate the near well failure, and we'll investigate the failure analysis during the gas production. Here we assume the two types of the fractures. In the stimulated zone, we assume that there is a main fracture, then around the main fracture, there are some small and local fractures. Then, when fracturings occurred, shale gas and reservoir gases comes in, and whereas the water comes in the stimulated zone, as well as water goes up due to the water injection. Due to the gravity, the water usually takes the lower part, and gases take the upper part. So gas and water can coexist. This gap actually due to the difference in the time scale between the flow and geomechanics. I'll let you review the capability of the T plus N, top plus or rock map. We employ the rigorous coupled flange mechanical modeling, accounting for the two-way coupled formal polar mechanics and dynamic multiple continuum approach. And we account for the tensile and shear failure simultaneously, and also we can simulate some leak off of the water to the reservoir formation from the full 3D flow simulation.
When you create the fracture and put it into the flow model,
Yes.
the fracture has thin dimensions.
Yes.
The grids in the flow model are, how do you know how to set the grids in the flow model?
Very good question. That actually related to the dynamic multiple continuum approach. So we have a single continuum, then we have a failure, then we generate the two continua, like a flow, run matrix, and the fracture medium.
But you'd have to do that after you've generated the fracture, right?
Yes. So, but in this case, well, if we are smart, then we can do that kind of things using the object-oriented programming. In this case, we generate a dual, for example, dual continuum model, but that dual continuum model can simulate the single continuum model first, then we hit some failure, then we change it. We can change it.
If I may add something here, in case you did not notice this earlier, what happens is that we check conditions at each node. If we have failure conditions, this node is split. So it's that done dynamically, so the fraction.
Geomechanical.
Yes.
Then how do you translate that? I thought you said earlier that the flow model, you couldn't change the rate.
Well, okay, I hear your point. We cannot change it, but Jikun will answer how this is done.
For example, can I draw? Yeah. For example, here is a single continuum for flow model. And then this is the one grid block. Then as a failure, we have two continua within a single. So actually for geomechanics, this is a single continuum. But for flow, we change it, the single continuum to a dual continuum.
So let me clarify this because you did not have a chance to do that. I discussed the mid process where you have flow and the matrix, right? What is happening is that in this particular case, you start initially and you assign very low volume to zero volume to that fraction. This doesn't exist. And then what is happening is that once you have that fraction evolving, initially the volume is very, very small, sometimes 10 to the minus 6 or so. It does not affect things significantly. So slowly, once you create the fraction, you start filling it up, and then the volume changes. Then the material changes. If you're saying that this may be introducing an error, that is, it's about an order of magnitude less than the convergence criterion, which is 10 to the minus 5. So initially, it's a very small error, but in the process, this is corrected.
which one? Shear failure?
You
Or?
don't have to go back. I just it's a quick question.
Mhm.
So, I mean, the corresponding strain condition that will generate the crack is,
Mhm.
is non-associative, or?
I mean, the flow rule, you mean?
Yes, yes.
We could use associative of flow rule or non-associative flow rule. So if the fraction angle is the same as the dilation angle, then there will be an associative flow rule. If those are different, then we have a non-associative flow rule. Yes. Okay. We have to investigate numerical characteristic for the non-associative or associative flow rule fluid models.
Volumetric change is pointing in one direction based on the more long surface.
No, this is. Mm-hmm. Oh. The first example is the hydraulic fracture. We have the fracture well, horizontal well, and we have some small fracture. And injection well is the 40 kilogram per second. And here's the dimension: 150 meters, and 150 meters, and 66 meters. And we have the following initial total stress conditions: S of capital H and S of D and S of small h's indicate the maximum horizontal and vertical and minimum horizontal total stress. And Young's modulus is 20 gigapascal, and Poisson ratio is 0.3, and tensile strength is 10 megapascal. Then we will investigate the fracture propagation for shale gas reservoirs. The dark area is the fractured area, and here is the x. Horizontal axis is x dimension, and vertical axis is g dimension. So during the water injection, the fracture grows up and down, but in a stable manner. When you look at the right picture, this figure shows the evolution of the fracture prone. The color bar indicates the time. So here, the fracturing occurs usually along the fracture tips. Here are the gas saturation maps. At initial time, the water is fully saturated within the fractures, but as time goes on, water takes the lower part, whereas the gas takes the upper part. So water is only partially saturated within the fracture. Let's look at in more detail about the aperture and water saturation and pressure along the center line. And this bottom corresponds to this point, and the top corresponds to this point. At the initial time, the water movement is almost the same as the fracture movement. However, as time goes on, there's a gap between the fracture propagation and the waterfront. So this inconsistency of the movement between the flow and geomechanics actually is in the difference in the time scale between the flow and geomechanics. Geomechanical responses are immediate, faster than the flow responses. These are the evolution of the flow and geomechanical parameters. With respect to time, this is the fraction node. So actually, during the water injection, we have failures, and this is the evolution of the pressure at the injection well. At early time, we have a severe oscillation due to the small volume of the fracture, and this pressure drops occur whenever we face the failure. But at late time, we don't see a severe oscillation because of the larger volume of the fracture volume. Fracture opening has the same behavior, and also we have uplift due to the water injection and reservoir dilation.
So is that fracture opening 0.02 meters?
0.02, yes, meters, so 2 centimeters here. Actually, yeah. No, this case, this is a synthetic case.
Seems big.
Yeah, seems big, yes. We define the damage zone is the area near the small or local fractures. Then when you look at the water saturation of the damages zone, and we have a high water saturation. Also, when you look at this water saturation at the second layer, and also we have a significant water saturation. So we can expect a significant leak-out of the water to the formation. We introduced electromagnetic geophysical simulation because it is sensitive to the water saturation. So then it complements the modeling of the micro-earthquake simulations. Then we can do some joint analysis of the flow, geomechanics, and micro-earthquake and electromagnetic simulation in the context of the reservoir characterization. Here are saturation map at early and late times. And we consider the two cases. One is the nanofluid injection, and the other one is the brine injection. Nanofluid, it means that the electronically highly conductive of fluid, propant. Then we convert the saturation map to the electrical conductivity by assuming that the mobility of the water is the same as the mobility of the nanofluid or brine. And then we test two cases, a vertical cross electromagnetic simulation and horizontal well EM simulation. And left lane is for the source, and the right line is the for the receiver. First, we will look at the vertical cross EM simulation. Horizontal axis is depth, and vertical axis is the difference of the EM response compared to the background. At early time, actually we don't see any difference. But as time goes on and the water saturation goes up and goes up, then we see the significant difference of the electromagnetic responses for the nanofluid case and brine case. Here is a 10% difference, and here is the 1.2 difference. We have the same conclusions for the horizontal crosswell EM simulation. Here, actually, we have a 25% difference, and here is a 30.5 difference of the electromagnetic responses. Considering that the detection level is above the 1%, and in real case, we inject several times larger than the water, EM simulation is a promising tool to detect the abnormality for the hydraulic fracturing operation for risk analysis. Secondary example is the hydraulic fracturing for the vertical well. There is the vertical well, and we inject the water 90 kilograms per second. And here is the line source because of the vertical well, and we have some heterogeneity, having the strong formations of a burden having a 10 megapascal of the tensile strength, whereas we have a 5 megapascal of the tensile strength, and we have a dimension like 600 meters and 300 meters and 120 meters. And Young's modulus is a 10 gigapascal, and Poisson ratio is 0.3, and initial water saturation is 0.3. So during the hydraulic fracturing operation, we found, as we see, the fracture propagates horizontally and downward, but there's no fracturing the above because of the strong formation. And also, when we look at the pressure response at the injection point, actually we don't see, it's a very little oscillation, it's almost invisible. To model induced seismicity, we used the seismic moment tensor analysis. M sub PQ is the seismic moment tensor, and small sub m PQ means the seismic moment tensor per unit area, and sigma is the fractured area. Then seismic moment tensor can be calculated from the elastic moduli and displacement vector and the normal vector to the fractured area and the new fractured area. Just like this. Here is lambda is the first Lamy constant, and mu is the shear modulus, and delta sub PQ is the second order identity tensor. Then we can calculate intensity of the micro-earthquake using following equation. This is the result from the simulation of the micro-earthquake. First graph is the scatter plot of the micro-earthquake event. This distribution can reflect well the fracture shapes. And second and third figures are the intensity of the micro-earthquake with respect to time and distance. So this value is reasonable, so it is promising to use for the reservoir characterization. For the vertical, here we simulate failure here we investigate the vertical well failure actually in the case of the cementing job, in the case of the incomplete cementing job. Here we assume the open injection well, and here is we have some cemented vertical well, and we have the following domain. First is the well casing, and we have the cemented and casing contact and cemented area, and we have reservoirs. We have the same properties of the hydraulic fracturing for the case of the horizontal well, and we have a constant bottom pressure, 30 megapascal. We take a 10 megapascal of the cement, and when we have a complete cementing, then we have the cohesion of the we have a 10 megapascal of the cohesion value in the contact area. When we have complete cementing, then there is no failure. But however, if we have an incomplete cementing, then there is some significant failure along the well. The final case is that we investigate the failure analysis during the gas production. We assume the following case. One is the longitudinal fractures, a long longitudinal fracture, and multiple horizontal well fractures, and multiple transverse fractures, and here is the horizontal fractures. For the long fractures, we can reduce the 3D system to the plane strain to the case. We first simulate assuming the elasticity. Initial pressure and total stress is 68.5 megapascal. The constant bottom pressure is 20 megapascal, and Young's modulus is 1.28 gigapascal, and partial ratio is 0.22, and friction angle is 0.5 radian, which is the 28.9 degree, and we assume the cohesion is 4 megapascal, in which we assume the weak reservoir. And here is the lambda is the indicator for the potential failure. If lambda is greater than 0, then we assume that area is the plasticity. As you can see here on these areas, in this area, lambda values are greater than 0, so then we can anticipate any potential failure. Based on the elastic simulation that we performed, the elastoplastic simulation for the case of assuming the shear failure. At all the time, we have a failure near the fracture tip. Then suddenly there's some failure in the middle of the domain, far away from the fracture tip, then those are propagated to the right boundary. On the horizontal well is the same thing. Actually, fractures propagate with two branches, and two branches propagate to the right boundary. But when we have a low perturbation of the effective stress, fracturing may not occur. For example, when we have 0.8 of the BO coefficient, or we increase the bottom pressure, then there will be very little fracturing. However, when you reduce the fraction angles, then we also see the significant behavior, significant fracturing, even though we have a 30 megapascal at the bottom of pressure. So actually, secondary fracturing during the gas production depends on the flow and geomechanics parameters and production scenarios. To summarize, we developed an integrated coupled flow geomechanics and geophysical simulator, and fracture propagates faster than the water does, and gas and water can coexist. And EM and MEQ modeling are promising tools for reservoir characterization, and complete cementing job is required to avoid a potential failure along the vertical well, not damaging the drinking water zone. Also, secondary failure can occur even during the gas production. Yeah, let me finish my talk. Please ask me a question.
You have to account for the existence of fractures in every grid block before starting, because you're not adapting the mesh dynamically. So in every point in the reservoir, there could be a fracture. You're not refining the...
Actually, conceptually not. No, just this is the fairly intact rock in this case. So we could include just like introducing some heterogeneity, for example, the cohesion or friction angles. Then that heterogeneity may account for the kind of existing some low and micro fractures.
The issue is addressed by having a fine discretization. So in essence, you have quite a few grids to split basically. So that's, instead of adjusting the grid, you have quite a few grids. The idea is that if you have high frequency, you can capture the distribution, the evolution of fracture quite well. This is what you're just referring to is on the major issues, and actually there is a major push right now to develop new techniques to be able to track the information evolution of fractures in an almost arbitrary way. That's not an easy problem, and what Chikun is showing you is probably the most advanced for the cutting edge, but it's by no means the good the ultimate solution. We need to do a lot of research in this area. That's what we're doing right now. And as with everything else, we'll have Bobby funded. Okay, Bobby?
So is your fracture simulator truly 3D? Can you do stress shadowing?
I'm sorry, it's like...
Is your geomechanics one truly 3D? So can you
right.
do stress shadowing?
Yes.
Yes. That's a yes. Having said that, but we're by no means... I mean, the major problem with geomechanic simulators is unlike flow, we cannot do easy laboratory experiments to confirm them. So what has happened is that Jikun has not shown this, but there is a confirmation against analytical solutions. But as in most geomechanical simulations, you go there with a hope and a prayer because there's no way they can verify this from what you see happening down there. There is no way to monitor the fracture. There's no way to see where the fracture is. So you hope that it's good, and you hope that by following the best geomechanics, geomechanical concepts and mathematics, you do it correctly. But the verification issue against analytical solution has been addressed. But validation against field data, we don't know. And no, if anybody says that he can do it, he or she is lying.
You can just crack rock at the surface.
Yes, you can. But what's happening is that we try to do this in the laboratory, no, because we tried. The boundary conditions are such, and the volume of rock is so limited that we don't know if I mean, okay, we can match what happens in the laboratory. We brought in a cubic meter of rock, and we did that. But the boundary conditions are very different. And so the best we can say is that against, we can confirm the validity in a limited volume of rock under laboratory conditions. And the idea is that because this is confirmed, we expect to do a good job down there, a few thousand feet. That's the best we can say. We cannot go past that. And this is the weakness of every geomechanical
I can
code.
say the same thing about
Yeah, well, okay. You're right. But you know, it's easier to control permeability than it is to control these things.
So did you compare the fracture propagation solutions you have there to commercial finite element code, just to see how they compare?
Commercial finite, not yet.
Okay.
But actually, we are working on the field case studies, and then the recent study that this simulator is pretty much promising to match some real test case. I cannot tell you more, but actually, it provides a pretty much good result.
Well, at the risk of sounding, well, you use the right word for this, I would have to say that the analysis we put in our code is it's more complex than what you can find in most of commercial fracturing. So we don't mind doing the comparison, but the question is, well, with a clear understanding that we're not comparing against something we consider correct, but we compare against something that's available.
Okay,
We have not done that yet.
Yeah, because a lot of people had problems with doing fracture propagation in geomechanical code as opposed. I mean, I know people have struggled with it for a while.
It's not an easy problem. This is what you're saying, but you're absolutely right. So it also what's happening is they made a lot of assumptions, simplifications, which we do not, because we say up front, this is a code that's not intended to be anything other than a research code. We try to look at any possible mechanism. We include this, we don't discount anything, and in the process, we may find some are important, some are not important. The price we pay for this is that these are very slow simulations. So to do what Chikun was showing you over here, we're talking about easily a week of continuous execution time or so. Okay, maybe more sometimes. So that's one of the reasons we're getting more and more into parallel processing, because these are very demanding. We're right on time.
What?
55. I mean, my God.
Oh, we're ahead.
We're ahead. How much? We're ahead? I thought we were, oh, sorry. Oh, I'm off by an hour, sorry.
Half an hour.
Okay.
So, how's the discussion? You gonna join me?
Of course.
And you, Dr. Zonak? Thank you.
Thank you so much. So what we presented to you today is not the ultimate solution to everything by any means. What we present to you today is the results of a 3-year project funded by RIPSI. So I think we made quite a bit of progress, but we would be perjuring ourselves if we made the claim that we answered all the questions. We understood some things better. We found new things which we did not expect, and at the same time, we opened up new areas which probably need to be investigated more in the future. That's how I see the whole thing. Tomas?
I'm going to take notes real quick.
So, what we're making available to you are basically all the results that you saw. In addition to this, the other thing that we're making available to you in the near future, because as I said, we're finishing the user manuals, are these codes. They can be used for very large type of simulations or very small, depending on what you want. Actually, by the end of the year, we'll release a version 2, which will include the parallel processing, so it can be used for clusters. Because all of these, if you get to the 3D medium grid looks, is basically nothing. Fortunately, for just the flow part, these do not take very long. I mean, by another meeting within a week you're done. But the idea is that will be a new version will release going to be called Unicode. That basically means you can use the exact same version on a machine that has just one processor or a supercomputer that has 10,000 processors like the ones we have at Berkeley. And actually, with your desktop right now, that is a powerful machine because every desktop has anywhere between 4 to, well, 16 processors right now. There's not a single processor machine anymore. So we can make full use of that in the next version we'll come up with. And this is available to you, and what I said is that not just the executable, but we give it full source code.
This will be available down the site?
Yes. Now keep in mind, if you are a research institution like a university or so, the cost is like $500.
He's a Ramco.
If you are a Ramco, it may go up to $2,000 or so. Again, it's nothing compared to what you get for a commercial simulator. The basic idea is you cannot try to make money out of this. By the way, we as developers make nothing out of this. So there is nothing there. There is no financial interest for us. Okay? This is all going to enhance the financial stability of the great University of California and Florida National Laboratory. We don't make any of this money. So. But this is, it's even if we have a collaboration with you, you are a commercial outfit, you get it for free. Okay, so there are different layers of cost for these simulators. Okay, some of them, for example, are very demanding, not for these scales, but they go up to $65,000 or so. And several companies have bought some of our very complex simulators that we have. Okay? But generally speaking, the cost, if there's collaboration, is not zero. If there's no collaboration, again, if it's a U.S. institution, like a U.S. university, it's something very, very minimal. If it's an international university, a bit more. If it's a U.S. Company, it is a U.S. registered company is another price. And if it's a foreign company, then it's another price. But it's very, very reasonable. It's nothing like what you would pay for. By the way, you also get free upgrades. In addition to this, there is no limitation on what you can do with this. I mean, in the sense that you can take this and change it to lines of code and sell it under your name. Who will not like it, but as long as you say that this came from Berkeley, we made the change, it's fine. There's no, in addition to this, no limitation on how many machines you can use it on. So if Aramco puts our codes, buys one code that puts in 4,000 machines, it's fine. Yeah, it's a different process. Very different, but we're not out there to make money, that's the basic idea. The idea is that this was developed for the benefit of the industry, the U.S. industry, and competitiveness, so it should be made available to everybody. And that's the way. Any questions?
Okay, are we ready to?
As far as REPSI is concerned, as far as the government is concerned, is this the end?
No, this is not REPSI. REPSI is not government, actually. REPSI is
you.
But your funding is over.
Yeah.
So if you wanted to continue this work, it have to be open.
Then we have to find, I mean, everything we do is public domain.
Right. But
So
it still has to be a whole new.
We have to find this is how research works. We do investigate a particular item, then we publish our results, but inevitably in the process we find something else that needs to be investigated. So, as you saw, there are several leads over there, things we want to do. So this is what we do. We just, do the regular misery and drudgery thing. We'll write new proposals, and Bobby will fund us. Okay?
But the funding for this particular project is done now?
It ended in December, actually.
We got
Somebody in the room continued to spend money without knowing it, but that's okay. That was me.
That's okay. But we've got a no-cost extension until now, so we had a chance to organize ourselves for this technology transfer. It was no-cost extension, but theoretically, today, at the end of this month, the project is over. However, that does not mean that our obligations stop.
as far as we can see, legal and moral as opposed to legal obligation. So if there's something that needs to be done in terms of adding information to our database or completing, you know, the user manuals or whatever else needs to be done, we will do this, basically because it's our name and our reputation. So we said we would do something, we'll do it.
Okay, well, let's engage the audience really quick and get a few of these points. You can see my style is to take notes. So who wants to volunteer? Sort of the first thing is discussion of what we saw. Is there anything additional? Next is what is needed, and then any recommendations you might want to make. And I think from here on, everything we talk about is the technology, not RIPSI or the food or conference room, whatever. We have a much nicer conference room than this, but they were taking photos in it, so we got bumped out of it. But I kind of like this room for sentimentality purposes. And that room's on the 9th floor, so you can sort of see things other than the roof of the old building. Who can I pick on first? Mark? Anything you saw you want to change? Anything you changed you want to saw? You like that? Yeah.
Well, I noticed you know you had that one cell that was kind of the typical cell that you said, I guess it's like symmetrical. You replicate the whole thing.
Oh, the stencil.
Stencil. Yeah, I mean, and you said that covers most geometry, except it wouldn't cover if it's not.
Except what?
It wouldn't cover if it was orthogonal.
So you just pass this guy around so the people on the phone.
I can tell you up front that we know quite well cases under which this would not apply, and this is if you have an inclined system, because it's not the same anymore. In this case, what we did, we found was that we get a very reasonable, extremely reasonable approximation, within 5% or so. If we investigate 4 or 5 stencils from the toe to the heel, you get 4 or 5 of those, in essence, you get an idea, you get a curve, and that describes within 5% the accuracy of the entire medium. So in this case, it would not be applicable. It would be, you know, you don't use just one stencil multiplied by the number that cover the entire system and make this.
Just so we ensure that the guys
Make this representative, but you can approximate it very, very well. Now, this is certainly not the universal solution, but you're entirely right. There may be possible situations where this doesn't apply, in which case you've got to go to full 3D or find a way to simulate or to play an approximate system, smaller system that can give you a very good approximation.
And also in that stencil for the planar fracts and the natural fracts, could you just make a grid and then you just sort of connect them together?
No. With native fractures, in essence, you do not represent individual fractures.
Oh, it's treated as
You represent the effect of individual fractures. As this is a linked approach, okay? But you do not track individual fractures. In the case of a fracture at an angle, for example, this is what Femi did, the second presentation that Tom made today. In essence, when he had to simulate geometry, then it's not a symmetric system. In that case, a stencil can be found, but it's bigger than the one we find over here. However, what Femi did was he simulated the entire system. As you saw, it was millions of pixels. It was a kind of red cloud. He did not cut any corners there. He went full steam exactly because of what he said. He used a small stencil. He found that it was not representative, so he must do the entire thing.
Okay, who else? Any other discussion or results? We can pass the microphone around. David, I'm sure you have some comments on the statistical approach. I guess you and Mr. Mary spoke. Any guidance you want to provide? Or recommendations, either?
I think the approach right now is good to kind of see the bounds of what's possible. But when you start desiring to make predictions or forecasts, there needs to be some power belief imposed to constrain where the fracture network is going.
Okay, so some sort of constraint, and we discussed this.
Now this is what Adnan is going to do during his PhD, right?
Next. Bobby? Anybody? Herb?
I'd like to understand better what I should do with those horizontal fracts that
Very good.
you see. Is there a way for me to look for them in some kind of field data? Like microseismic or something that says, yeah, they exist. If I believe they exist, is there an easier way to put them in my prediction models that create multi-million simple models?
An excellent question. The first step in this direction was the expensive approach. By the way, what you just said is very interesting because there is a paper by Sulin and Nifsey, published in SB Journal, and in there, using some real data, live data, you can see that the angle, the slope is not minus 1/2. It is different. It's minus 1/3. So, this being the case, we have some indications that from several sets of published data that this is indeed the case, that it's not, we don't have minus 1/2, but how we can use this and how we can conclusively and uniquely tie it to particular type for the reason for that. For example, the angle of the fracture as opposed to interference with a nearby well. This has not been done yet, but it would be a great area to look at.
You mentioned how you can figure out if you have those horizontal fractures. When we used to do a lot of tilt meter frac mapping, now it's arguable how you interpret the data, but all the interpretations this company would do would always show some component of horizontal type fracturing, or would show it in a lot of cases. So there may be something there with deformation mapping, which you might need to extend the technology, but we're not using that often anymore. So there might be something there. One thing I was going to comment on is that this whole issue of non-uniqueness. If we can try to figure out how to provide some bounds on what the fracture geometries look like, we see a lot of work that goes all the way from primarily tensile fractures to primarily shear fracturing. You see people modeling fracturing as hydraulic fracturing in the sense of it's a shear fracturing process. If we could describe the hydraulic fractures a little bit better, and also we didn't hear a lot about profit, and where the profit is or the profit's not, these types of things, then we might be able to describe the production a little better. Because the other inverse is, if you could tell us exactly what the reservoir looks like, then we could probably back out what the fracture looks like. So that's the issue, is that maybe from the geomechanical work with the coupled geomechanical flow work, maybe we can tell a little bit more about what these hydraulic fractures look like and which areas to focus on. Are we focusing primarily on a shear process or a tensile process? I have my own bias, but that might be something to look at in the future.
Actually, it's an excellent point, and we may be able, doing just this, because there was another Ripsy project which is continuing until it's over. And in there, we expect that we'll have a chance to do just that. And for updates, the person to bother would be Jihun, because she's going to be in charge of all that, these issues. But these are areas that certainly need to be explored and need to be further clarified. Yes, we are. If you're saying indirectly that we're just scratching the surface, that's exactly what we're doing. That's exactly what we're doing. But before we can run, first we need to get off the chair. Then we need to walk. So we just got off the chair. Let's begin walking, and then we'll see. We may be able to run.
Okay, what about lightning round, Bobby? Oh, you got it. Okay.
One thing I see, all the examples that you gave there were using a stencil approach or a development approach. What they've gone through more recently in the field is the engineer's completion, not just geometric progression of the fractures. Along the horizontal level, we're actually trying to design it based on the law, structural measurements that they're seeing. So it's going to dramatically slow down the computation. I mean, you actually have to grid it up. And there's also the issue of whether you're bidding toe up or toe down. If that leg is standing on the water, you've got a dramatic difference in pressure, interbounding condition pressure, whether it's first the heel or the toe.
You're absolutely
several
right.
hundred PSI sometimes.
You're absolutely right.
And another issue there that we're dealing with now is capillary pressures. These extremely tight formations, they're shales. Capillary pressures are in tens of thousands of PSI.
Yeah.
Between gas and water systems. And even in the microdarcy stuff that we're looking at, like in the pocket, I've done a lot of work in the pocket. And it could be like 35, 40,000 PSI on a gas water system.
Well, right now we do assume pretty high capillary pressures. I mean, that's what we use. And the reducible water saturation, some of these shales is sometimes 75, 80%. Yes. So in most cases, I mean, not most cases, but in the cases we're allowed to look at data to take a peek, the reducible water saturation is like 75 to 80%, and the native water is 30% or less. This being the case, water is not mobile at all. It's actually one of the things we see in our simulations is the water slowly evaporates as gas flies by. Okay, so we can see that, but it's a numerical simulation. But I certainly take away the point of the capillary pressure and the need to come up with better numbers, better equations and better numbers.
Okay, go ahead, Stuart.
So I was just thinking through the coupling of the models, the mechanical fracture model and the simulation, and I was wondering about, do we start, when we start getting off the chair, do we start with the flowback data, the hourly data, as we go from water to some sort of hydrocarbon, and then as we move on into a little less water, how do we, I mean, do we need to start looking at that first?
So basically you're saying, can we, should we?
Should we, can we?
Yeah.
And then the other,
we should and we can.
I'm sorry.
We should and we can. But the very large part of our effort here in this project was to come up with the tools. We developed the tools. We have a first iteration of the tools. For flow, it's a bit more thorough. It's quite finalized. For geomechanics, it's something that needs several iterations. And as we know more, we're going to improve that. But certainly that'll be the next step.
And then the other thing I was going to comment on is intrigued by the carpless wave, the low energy wave.
Yes.
And just how do we progress that to something we might.
How do you spell it, George?
Krautklis, Krautklis. Actually, I hesitate to call this person Russian because the name sounds like Lithuanian, Estonian, something like that, okay? And these days, just calling him a Russian may be the same thing as calling a Scottish English, okay? You may not like it at all, okay? So,
What do we want to use it for? Sorry.
this is for fracture detection.
Okay.
If you're interested after the official end, whoever's interested, I can show some real laboratory data, very, very recent, that shows what's happening in this case.
Okay. I'll put a note that you ought to follow up.
I do look forward to the little PVT.
You have to come to the
Chrisman meeting.
The Chrisman meeting, the PVD.
Okay, so it is part of study.
It's not part of this study, no.
It's part of another project, but it'll be on the 1st of May.
Okay.
Or maybe the 30th of April, but it's probably the 1st of May.
But what has happened is that this was not part of the study. But in the process, we began scratching our head. And then we had a very good student that wanted to look into this. And we started looking into this, and we've been blown away.
Because as I told you, it can be off by 70% or 80% in your density estimation if you do not have the correct PVD properties. You know, methane, that's incredible what we see happening. Even something we think we know, like methane and ethane, no, we get 2 nanometer, 5 nanometer pore size, and it behaves entirely different. You can see it's liquid.
And those multi-scale transport phenomenon in gas, it is very interesting. Are you consider to do oil? Because now the industry, yeah.
You're hurting me, okay? Because what happened is that right before the announcement that Lipsy was decommissioned, Tom and I got a email telling us that congratulations, you won $2 million to study just that. So, fortunately, this is not over. So there is, because it's supposed to be fiscal year 2012 money, there is a possibility that they let us have it.
The easy answer is yeah, and some of the students had worked on that, but gas was really our focus for this project. But we have multiple tentacles out there trying to get an oil project funded.
This is funded theoretically, but we don't know if it will be, the funds will be released. There is a, I mean, they say there's a good chance that we'll get the money, in which case we'll be back in about 2 years' time to tell you what the results are.
We'll invite you now to help us with, this core lab's going to have all sorts of data that might enable this. You didn't hear me say that.
We do have a lot of data.
Yes, you do. The question is whether you share this data or not.
Well, there are avenues for that, but we would have to partner with them, or we'd have to partner with a company that has access.
Keep in mind, we don't care where the formation is, we don't care about the name, we don't care about depth, we don't care anything. Just give us the specifics related to the properties of the systems of the core and nothing else. You can keep the rest of the data to yourself.
Bias? Okay.
I was wondering, so we saw these multi-physics, all physics included models, and they take a long time to run. And I was wondering if you guys had in mind in an upcoming study to look at a sensitivity analysis, identify the most prominent parameters, and boil down sort of an easy version for everyday use.
Well, I can tell you that here is the situation. At least for us, our mission in life is to address the new generation of scientific problems without ever competing with the private sector. The basic idea is that we are not in the business of developing something which can be faster for the benefit of a, how shall I say, of several companies that may want to use this as the product which might compete with the private sector. We cannot compete because the last thing you want to do is have a senator from Kansas from the Department of Energy say, what the hell are you guys doing? Are you putting my guys in Kansas out of business because you want to develop a simulator? So.
I think he's really asking about control parameters, what dominates. And I think
asking about the simpler version, simpler, faster version.
No, he was.
I'm asking about both.
Yeah.
No, simpler, faster version. Well, if this is the case, we have a pretty good idea what slows down what. Okay, very good idea. Okay, so we can tell you up front what slows what, and we can tell you how you can make it run faster if you want that. But that's straightforward.
I don't think what he's asking is for, and again I'm repeating perhaps, but you're asking us to help design experiments that will show that for 35-degree oil, maybe it's not practical to produce that at this time. I think that's a conclusion that your sensitivity study would reach. And it could be because of flux in the reservoir, it could be because of wellbore hydraulics, it could be because of all these things. But once you put the floor at 35 degrees API, that's going to chop off how much of what play. I don't even know what Bakken is. What's the gravity for the Bakken?
It depends. 40 plus.
40 plus, yeah. So I just made that up. But for example, right now we've got poor performance in Vaca Muerta wells. And Vaca Muerta is supposedly the best play in the world, other than that Russian thing that obviously now nobody's going to jump into. But, you know, if there were ways that we could identify what the key parameters are from modeling, that might be a real help there. I see your point, and I think George is thinking more along the lines of just simplification, which obviously is something we did have all the students try to incorporate, but ultimately, I don't really care about simplification because computers out here is free, but
exactly. We
but
don't care about that.
the understanding of what makes a play, I think that's going to be critical. What if you ask me what keeps me up at night is why is the Eagle Ford, the Niobrara, and the Bakken at present, the only profitable, liquid-rich, like, well, Wolfcamp is obviously, but I guess I'm going to argue what its nature is. Utica's struggling. Somebody throw me a bone. Oily part of Barnett, I guess, is okay-ish. Oily part of Marsalis, I don't know if it's making very much. Is there anything else? Monterey's out there, but is that even an analog? I don't know.
Monterey
I think
is
you get the
different
ones
world.
that are dominant ones that make a little.
Sorry?
You get the ones that are dominant, make a little bit of money.
Yeah, well, there's some shale in Canada, right? The layered shale that supposedly is this monster, but it's also got all sorts of problems. Apparently, it's like 17,000 feet deep or something.
To use the same analogy, but thinking about gas, what keeps me up at night, which doesn't, but anyway, is the fact that the recovery from Niobrara is 3% to 5%. If we can bring it out to 15, that's where the fun is. And to do that, basically you do what we're doing, which is research. So we make no assumptions. We don't know a priori what's important and what is not. In addition to this, as I told you, our focus is mainly research. So for research type of simulations, even if it takes a week or 2 weeks to run the simulation, it takes us half a year to analyze the results and write the paper. So it's not that important for us, okay? That's why one of the very legitimate uses for our codes is to give it to the industry, and then they strip out what's important and use this in their simulators, whatever. It happens all the time.
But even for research, it's always good to have a good understanding of why things happen, so you can boil it down
Exactly.
to intuition.
In the beginning, we did not know anything. Now we begin to get a feel. To go one step further along the same lines, we have a code for shale oil. What we're finding out is by far the most effective.
Guys, they're still going to be having this talk 30 years from now.
Yeah.
I mean, we know that. We will still be around. We'll still be throwing out ideas and everything else.
Speak for yourself. Once I retire, I retire.
This is a long, long process. Go ahead, David.
But let me complete my answer. What I was about to say is that we find out that by far the most important thing is fractures. Everything else, in flight gas, you can push gas drive, you can use thermal, it can do okay, it can improve production, but nothing gives you improvement in production higher than the availability of extensive fracture system. End of story. There we know. End of story.
Two parts. Talking about field development, I would really be interested in seeing more work about how the dynamics of multi-well systems operate and what kind of effects does a multi-well system have versus a single well system. So we have to make these decisions before we drill anything. So spacing is an issue, of course, but how does it change the, let's call it late time or boundary dominated flow when we start changing the spacing of these wells? And then part two, in oil shales or liquids rich shales,